Hi, welcome back to Statistics 1. We're up to Lecture 9, and today we're going to do multiple regression analyses in R. So in the last lecture, we walked through multiple regression, the regression equation, how the regression coefficients are estimated, and I showed you a little bit of matrix algebra so you could see how they're calculated if you wanted to do that by hand. But of course, we just want to put our data into R and let R do the work. So what we'll do today is we'll write a script that runs a multiple regression analysis in R. I've organized this lecture into two segments. So in the first segment, we'll run a first multiple regression analysis. And then in the second segment, we'll do the same analysis over again, but we'll get the standardized regression coefficients. And in that second segment, we'll do some model comparison. So we'll run multiple models, and we'll run some R code that allows us to compare the amount of variance explained by each subsequent model. So in the second segment, it's going to be standardized, and we'll do model comparisons. But first, let's just start with basic multiple regression analysis. So we'll do that in segment 1. So the goal of this segment is, again, to follow along. This is one of the lectures where I want you to follow along and try and write this script for yourself in R, because the next assignment will be just like this. You'll have to write a script that does multiple regression analysis. So first, what we're going to do is just run a simple regression. We'll just put one predictor in the regression equation, and then we'll do multiple regression. And we're not going to get crazy. We're just going to put two predictors in, and just to see what happens when we add in a second predictor. And for this analysis, I just made up data. This is an example I've used several years now in my classes because it has sort of a unique feature to it that really illustrates and drives home the importance of sort of watching your regression coefficients as you take out or put in other predictors. Sort of some unique things happen with this data set. So I like this example, and it's pretty intuitive. So the idea is that we're just predicting physical endurance among an adult sample. So the ages of people in the sample, I believe, ranges from around 30 up to about 70 is the highest. We'll see when we look at the descriptive statistics. And we're looking at physical endurance in this group of people, and we're just going to look at two predictors. One, what's their age, and the other is how many years have they been engaged consistently in active exercise, and I call that active years. This is an interesting data set because as age increases, physical endurance decreases, but if you're engaged in physical activity for more years, so if you have more active years, then your endurance goes up. And the older you are, the more years you have to be involved in active exercise. So there's some complex relationships going on just among three variables. So it's an interesting data set. Again, I made the data available on the course website. This is the fourth example that we're walking through in a lecture, so it's Stats 1, Example 4. Again, we'll start off our script with just some lines of code. So this is Lecture 9. We're just going to do a multiple regression analysis. And again, like most of our scripts, one of the first lines of code is the read table function. I'm going to take this data file and read the contents into an object that I'm just calling endure, E-N-D-U-R. Just come up with these things sort of randomly. You want to keep them sort of short because you have to write them repeatedly in the code. The first thing I'm going to do in this script is look at some scatter plots. As I said, probably physical endurance decreases as a function of age, but let's look at that in a scatter plot. We'll also look at physical endurance as it relates to active years. I'm jumping right into the scatter plots here in this script because there's a lot to do in this script to get multiple regression analysis, to get the output, and look at all the regression coefficients. But remember, if we were doing this with our own research and we were being thorough, we would want to test all the assumptions leading up to this. I'm skipping that now because we've done it in previous examples. You've done it in previous assignments. But remember, we're assuming univariate normal distributions. We're assuming linear relationships among variables. We're assuming homoscedasticity, reliability, validity, and so on. Okay, but we're going to skip all that today and just jump right into the scatter plots. So this first scatter plot is looking at endurance related to age. And indeed, what you see is endurance declines as people get older. And if you look at the x-axis, you get a feel for the age of the people in this sample. So we have a big sample. They range from about 20 up to, oh, I was wrong, I said 70. There's actually some folks up around 80. But the average is about 50 years old in this sample. And you can see the regression line in this scatter plot is negative, but it's very slight. It doesn't have a very steep slope, but it is negative. So as people age, their physical endurance scores drop. And this physical endurance scale is sort of arbitrary. You see scores go from 0 up to about 60. It's just sort of an arbitrary scale. Let's also look at our outcome variable physical endurance as a function of active years. Here we expect a positive correlation. And indeed, that's what we see. So if we look at this scatter plot, we see a positive slope, positive regression line, and it's a bit steeper than the previous function. So that's suggesting that the relationship between active years and endurance is stronger than the relationship between age and endurance. But let's see that in a multiple regression analysis. So the first thing I'm going to do is run simple regressions so that we can compare those models to the model with both predictors in the equation. So the first thing I'm doing is running a simple regression predicting endurance from age. Again, the function to run this is LM for linear model. And it's simply LM y tilde x. The y variable is endurance. It's in the data frame endure. So it's endure $endurance. And the x variable is age, again in the data frame endure $age. I put the results of that in a new object that I called model 1. So I came up with that name, model 1. It could be anything. And then I use the summary function in R to print the results of that regression analysis. And here's the output of that analysis. What I've done at the top of this slide is I'm showing you the actual regression equation, right? It's y equals the regression constant, b sub 0, plus the regression coefficient for the predictor, b sub 1, times x1. x1 in this case was age. So 33.16 is just the intercept in this analysis. And negative 0.13 is the slope of the line relating age to endurance. Remember, it was negative and it wasn't very steep. So this is summarizing all the results of the regression analysis. Again, this is one predictor. So here are the coefficients that go into this equation. So the intercept is 33.16. That's just my predicted score on y when x equals 0. If you go back and look at the scatter plot, you sort of see how we would get that value. The next estimate we see is the regression coefficient for age. Again, that's negative 0.13. What that means is for a 1 unit increase in age, I'm predicting a drop of 0.13 on this endurance scale. That's not a big drop, right? So for every 1 year of age, it's only 0.13. If you remember the scale of the y-axis, it's pretty large. So you'd have to get 10 years just to get a drop of 1.3. There's a lot of stuff in here. I'm not going to cover all of it right now for the sake of time, but one thing to look at is the multiple r squared. Remember, that's just the percentage of variance in the outcome variable that's explained by the model. In this case, just the one predictor. But it's important to look at because what you see is we're not explaining a whole lot of variance here. Just really 1.5% of the variance explained by age. That's because there's not a very strong correlation between age and endurance in this sample. That's important to remember. So now let's do the simple regression using active years to predict endurance. So I'm just going to call this model 2. Same exact structure using the LM function and the summary function. Here I've summarized the regression equation at the top. I got that from this piece of the output. There's my regression coefficients. The intercept is the predicted score on y when x equals 0. Now it's about 18. But here what you see for the regression coefficient for active years is it's much stronger. So it's 0.76. Still not real strong. So for a 1 unit increase in active years, we're predicting not even a full 1 point increase in endurance. But if we look over at the p-value here, it is significant. And if we look down at the model R squared, we're now explaining about 11% of the variance in the outcome measure. So we're doing a lot better with this model because the correlation between active years and endurance is much stronger than was the correlation between age and endurance. Now what gets interesting is what happens to these coefficients when you put both age and active years into the equation. So that's what we're going to do in Model 3. Model 3, again, is just the LM function, y tilde. Now we have two predictors. It's x1 plus x2. Remember, this is a linear model, and it's additive. So we're assuming that the effects are additive. We can embed non-additive effects by creating interaction terms, and we'll do that in a couple lectures. But for now, we're assuming that the effects are strictly additive. So we're going to put in both age and active years, and let's see what happens. This is where I think it gets interesting. So our intercept is 29.4. That's not so interesting. It's just the predicted score on y when both x's are 0. But if you look at the regression coefficients for both age and active years, you see that each of them got stronger than when they were entered into the regression analysis by themselves. Right? So now for age, we're up to negative 0.25, or so round up to 0.26. And for active years, we're up to 0.91. That was around 0.75, I believe. Right? So each of them got stronger. That is, the age slope got steeper negatively, and the active years slope got steeper positively. That's a bit unusual. It's more common when you run a multiple regression analysis and you add in more predictors that each individual predictor gets weaker in strength. Because if you take it to an extreme, if you put in hundreds of predictors, there's only so much variance each of them can uniquely explain. Right? So if you put in lots of predictors, eventually they should all suffer. So it's a bit unique. This example where you've added in another predictor and they each get stronger. Why is that? Well, think about the example. So if we go back to the simple regression model where we were predicting endurance just from active years, what we saw was a nice, strong, positive association so that the more or the longer you're engaged in active exercise, the greater your endurance. And that was a pretty strong relationship. But what we're seeing in the multiple regression analysis when we add in age is that that relationship is even stronger. And what we see for age is the opposite. So age showed a negative relationship with endurance. And when we add in active years, it's getting even steeper and stronger in the negative direction. Now, why is that? You have to look at this sample and think a little bit about the characteristics of this sample. So if we look at the active years variable, these are people who are very physically fit. So if you look at the average, it's around about 10 years of being actively engaged in physical exercise. So, and again, these are people who range from anywhere in their 20s up to in their 70s. So if you're like me and you're in your 40s, and you know someone who's been actively engaged consistently in an exercise program for 10 years, that's pretty good. So this is a very active sample that we're dealing with. They're very physically fit. That's why when we look at just age as a predictor, we only see a very shallow slope and a very slight negative correlation, because these people are very physically fit, they're active, they're combating that effect of age. If we now take into account active years, what the regression coefficient for age is telling us is it's now the slope relating age to physical endurance for someone just with an average amount of exercise, so for an average amount of active years. And that's why it got a little steeper and shallower. The same goes for active years and endurance. There's a positive relationship between the two, but if we take into account age, and we consider the fact that this is sort of an older sample, that it's even more impressive, right? So that relationship between active years and endurance gets even stronger. And again, this is somewhat unique to this example. Not to say that it doesn't happen in research, but it's more common to see when we add in more predictors that the strength of each individual predictor tends to weaken rather than increase. So again, that's one of the reasons why I like this example. So here, to summarize, is the final script for that multiple regression analysis. Again, I had some comments at the top. I read the data into an object called endure. Again, I'm playing with my default settings to get my graphics pretty here in the video room. Then I did some scatter plots to show you the simple regression results. And then I ran 3 models, Model 1, Model 2, Model 3. I used the LM function and the summary function to get that output that we looked at.